There may be, there may be more than one force exerted on an object, but not every forces that produce work. For example, when we look at this figure, we can see that it is not only the force F that exerts on this object. We can have the weight or the gravitational force and the normal force acting on this object also. But the point is that the gravitational force and the normal force, as its name, is perpendicular to the direction of the displacement, right? This is the direction of the displacement, and in this case the gravitational force is perpendicular to the displacement, and the normal force is always perpendicular to the displacement for an object moved on a surface. So it means that in this case of the gravitational force and the normal force, we have that for the gravitational force mg and the normal force n, theta is equal to pi over 2. So if theta is equal to pi over 2, we have that cos theta is equal to cos of pi over 2, which is equal to 0. So it means that there is no force there is no work from the force that is perpendicular to the displacement. This is very important result. If you know there is some forces act on an object and the direction of the force are perpendicular to the direction of the displacement, we know that the work done by those forces are 0. Okay, so before we go on, let's make it clear about the language when we talk about work. From the definition, work is the influence of the environment to the system. So it is a kind of interaction between the environment and the system. So when we talk about work, we have to specify what do the work and the work done on what. Okay, so it means that when we talk about the work, it is not only much you identify the system, you must also identify what agent in the environment is doing work on the system. When discussing work, always use the phrase the work done by on. After by, insert the part of the environment that is interacting directly with the system. After on, insert the system. For example, the work done by the hammer on the nail. You can see that this is the work done by the hammer. So the hammer is the environment that do work, and the system is the nail. So the work done by the hammer on the nail identifies the nail as the system, and the force from the hammer represents the influence from the environment. The next thing that we have to be careful is about the cause of the displacement. We can calculate the work done by a force on an object, but that force is not necessarily the cause of the object's displacement. For example, if you lift an object, negative work is done on the object by the gravitational force. This is very important case. You have an object. You lift this object by some force F, but you know that there is the gravitational force mg. Okay, but if the object moves upward, so the cause of the motion here is the force, force F. But we also have the mg, that we can look at the environment that exerts the force to this object. This force mg is not the cause of the upward moving of the object, but we can still calculate the work done by the gravitational force. And you can see that the work done by the gravitational force in this case, Wg is negative. Why? Because the angle between the displacement, the angle between the displacement and the gravitational force is equal to pi, or 180 degrees, and cos of pi is equal to -1. Okay, that's why we have that the work done by the gravitational force is negative. This is interesting. You can see that we can calculate the work done by the gravitational force, but the motion is on the opposite direction to the gravitational force, and we have the negative work of the gravitational force. Next, let us discuss the mathematical tool that we can use to express the work. This tool is a scalar product of two vectors. By definition, if we have vector A and B, we define the scalar product of A and B and use the symbol A dot B, and sometimes we call the scalar product as a dot product. So the dot product of A and B, or the scalar product of A and B, is defined as AB cos theta. A and B here is the magnitude of A and B, and theta is the angle between A and B. So from this definition, you can see that if we put delta R as vector A and the force as vector B, we can have that F dot delta R is equal to F delta R cos theta, which equal to the work. Okay, so we can write down the work in terms of the scalar product of the force from the environment that exerts to the object and the displacement. We can see from the definition of the scalar product that when we do the scalar product between two vectors, the result is a scalar. So, when we use this to the definition of the work, we can see that work is a scalar. Work is a scalar quantity. Although, by definition, we define the work in terms of two vectors. Work is a scalar. There is no direction. There is no direction associated with it. All types of energy and energy transfer are scalar. We will see later that work is nothing but the energy transfer. So, we can see that all types of energy and energy transfer are scalars. This fact is a major advantage of the energy approach because we don't need vector calculation. This is very important. And you will see later that when we can avoid the vector calculation, many problems can be very easy. So that is the advantage of the concept of the energy.